Welcome all of you there in the virtual land for the distinguished talk this morning, this afternoon or night. Good day or good evening to everyone. The talk today will be given on the subject of optical receivers in CMOS by Professor Filip Tavernier from the Catholic University of Leuven in Belgium. I advise you that please stay tuned to this channel, subscribe it. You will be able to see future announcements, future webinars organized by Solid State and EDS joint chapter of IEEE in South Brazil. So this distinguished talk series is promoted for hot topics in circuits and devices by this IEEE chapter, which is rather young. We are just 1 year old. During this second half of 2020, we'll have several seminars, and we started the series in last June. And given the pandemic situation we are living in, we are streaming out in webinars so that you can participate in these hot topics. Please interact with questions in the YouTube channel, and right now live, and the speaker will be able to answer those later on at the end. The speaker, Filip Tavernier, let me say a few words. He has a master and PhD degree from engineering science from the Catholic University of Leuven. He was during 2011 and 2014, senior fellow in the microelectronics group at the CERN, the European Organization for Nuclear Research in Geneva. After a period in postdoc in the Department of Electrical Engineering in Leuven, Catholic University, he joined the faculty as an assistant professor for the last 5 years there. Professor Tavernier's research interests include circuits for optical communications, data converters, DC-DC converters, and chips to operate in extreme environments. He is member of technical program of several distinguished and very important events like ESCIRC, SPCI, CICC, and he is guest editor of Solid State Circuits Letters and coordinates European webinars for solid state circuits. On behalf of the chapter and all my colleagues, we are 5 coordinating the chapter here. We thank you, Filip, for agreeing to give this talk and share these very interesting ideas of integrating optical receivers to CMOS. So the floor is yours, and hopefully that will be an exciting period for this topic in our solid state circuits field.
Thank you very much, Sergio and colleagues, for the kind introduction, for the possibility to showcase part of my work in optical receivers in CMOS. I'm a professor at KU Leuven in Belgium, and the topic of today's talk will be, as the title slide already says, optical receivers in CMOS, a quite interesting idea, I must say. So here you can see the outline of what I would like to go through with you today. So let me first give you a short introduction. And after that, let me introduce you to integrated receivers in CMOS for 850 nanometer communication. This is the more traditional approach. Now, the novelty in the work that I will present today is mainly in the third bullet point, so integrated receivers for 1310 and 1550 nanometer light. This is a typically used telecommunication wavelengths, and those were not possible to do with CMOS because silicon is not sensitive to those types of wavelengths. And we found a way to work with those types of wavelengths. So that is what I will discuss in that third bullet point. After that, I will come to some conclusions and future work for this topic. So as an introduction, free space optical or optical in general communication is almost everywhere. It starts very simply from your infrared remote to control your television, point-to-point wireless optical communication systems, where a high-speed wireless communication link can be made between two base stations, for example, between 2 towers in a very busy city. You don't need to dig the street open for a very high-speed link to be made between those 2 base stations. Also inter-satellite communication, where a laser in one satellite is focused onto a photodiode in the other satellite to establish a high-speed wireless link. Or more recent and more interesting for consumers, Li-Fi for light wireless communication, where your LED light bulb can also be modulated at high frequencies to transmit data, very local, to a consumer device, a smartphone or something similar below or in the line of sight of that light wave. Now, clearly, the advantage is already here. So you can go to very high-speed data links, but you need line of sight. You almost always experience that when your infrared remote does not have line of sight with your receiver. Now, of course, engineers have found a solution to that, and that is, of course, guided light communication. For that, you need optical fibers. Here you see an example of an optical fiber, or actually a set of optical fibers in a single wire. And the principle of an optical fiber is, of course, to use a glass fiber to conduct the light. And glass with the core and the cladding having two separate refractive indices, N1 and N2, can act as a waveguide. And if the impinging light, the red arrow, impinges on the surface between N1 and N2, the core and the cladding, below a certain critical angle theta c, the principle of total internal reflection, or TIR, is experienced. And all the light power is sent back into the core. And as you can see here, indeed, we can send light around corners over very, very long distances, because now the light remains focused and the light can go over, around bands. And also this glass is extremely pure, so there is almost no absorption of light in this glass fiber. This is a principle of optical fiber communication. The advantages is, or one of the advantages is that there is no line of sight required anymore, and that there is extremely low loss in these glass fibers, so we can go to extremely long distance communication. So if we have a closer look at loss in glass fibers, it can be seen here. So on the y-axis is the loss in dB per kilometer as a function of wavelength of the light that you try to transmit through that glass fiber. And what you see is that there are these types of optical windows, regions, wavelength regions, where the loss is minimal or low compared to the wavelengths around those windows. And as a result, engineers have made certain optical windows. For example, the O band, the original band, around the wavelength of 1,300 nanometers is located here. And nowadays, losses of around 0.5, 0.4 dB per kilometer can be achieved, extremely low. A second optical window is, here it is called the third optical window, because the first optical window is what I will discuss last. This other optical window around 1,550 nanometers is called the C band, the conventional bands. Then there is a long wavelength band, a slightly longer wavelength. And then there is this first optical window, the 850 nanometer band, which is a bit special in the sense that it is a primary band for multimode fiber systems, which are used combined with VCSELs, vertical cavity surface emitting lasers, and silicon photodiodes. And this is, for our storyline of today, extremely important to start with, because traditionally, if you work with silicon, with CMOS, this is the only viable approach you can have. You cannot do anything here. At the end of this talk, I will convince you that we can also do something here in these wavelengths with silicon, with CMOS. So a short introduction about the optical fiber types. There are mainly three. The first two are shown here. They are both constructed of glass, very pure silica glass. And the first one is a single mode fiber, where only one mode, one optical mode, typically the hybrid mode, HE11, can be transmitted from the transmitting end to the receiving end. In order for that to happen, the core diameter, this white region here, needs to be extremely narrow, around 8 to 10 micrometers. The advantage of having only one mode is that there is no modal dispersion, which is the case with a multi-mode fiber. There are several propagation modes that each have their own propagation length, and as a result, each of these modes will arrive at the output of the fiber at slightly different times, and this leads to intersimple interference, or here, or for this specific purpose, called modal dispersion. This is not the case with a single mode fiber. As a result, a single mode fiber obtains very high speed distance products. For example, 100 gigabit per second over 40 kilometers is not an exception. But of course, it is difficult to align due to this very thin core. A multi-mode fiber has a thicker core, multiple propagation modes, has modal dispersion, and is a typical fiber that is used for 850 nanometer light communication. It has a modest speed distance product, for example, 50 gigabits over 100 meters only, and of course, it's much easier to align. There is a third interesting, especially if you focus on CMOS integration, interesting optical fiber type, and that is plastic optical fiber. As you can see here on this figure, a single mode fiber and a multi-mode fiber are very, very small. The core area is very, very small. While a POF, a plastic optical fiber, is huge compared to it. It has a core diameter of almost 1 millimeter, which of course makes for an extremely easy alignment. Therefore, assembly and construction is very easy to achieve. Now, one of the drawbacks is that you need extremely big photodetectors, especially if you want to integrate them on a chip. This requires a lot of chip area, a millimeter here, so this is expensive. Another disadvantage of plastic optical fiber is that the loss, the attenuation, the dB per kilometer attenuation is extremely much higher than glass fibers. We're talking about 100 dB per kilometer. So this is only a viable approach for short range communication, like in cars or for industrial applications, where vibrations require that the photodiode and the fiber is not extremely thin, narrow as with a single mode fiber. So shortly comparing optical versus wireline and wireless, compared to copper wireline, optical communication is prone to much lower loss. It also has much higher bandwidth, at least the channel is much higher bandwidth. Also, an optical fiber is much lower in weight for the same data capacity. On top of it, it is not susceptible to electromagnetic interference. Compared to wireless communication, also the loss is extremely much lower. There are much less security issues, and there is no spectrum congestion. This plot shows, as a function of cable length or distance between the receiver and the transmitter, and data rate, where optical can be localized. And this is at high speed and long-range communication, or relatively long-range communication. But there is a big but here. It is an expensive means of communication because you need to convert your electrical domain signal to an optical domain signal in the transmitter and back to the electrical domain in the receiver. And this is a difficult thing to do or leads to a high cost. So if we compare 850 nanometer links versus 1310 and 1550 nanometer links, the typically used telecommunication wavelengths for optical communication, you see here that they differ both in the laser diodes, the fiber, and the photodiode, so the transmitter, the communication medium, and the receiving part. For 850 nanometer, we typically make use of VCSELs, vertical cavity surface emitting lasers, which are quite cheap. We make use of multimode fibers, which are also quite cheap and easy to align. And we can make use of silicon as receiving material because, as we will see, silicon is sensitive to 850 nanometer light. This is not the case for 1310 or 1550 nanometer. There we need to make use of more expensive laser diodes like Fabry-Perot or distributed feedback lasers, which also consume a lot more power than VCSELs. Moreover, we typically make use of single mode fibers, and we need to make use of germanium or InGaAs or indium phosphide as a detector. So this is the difference between those two major link types. So the story I would like to further disclose to you today is the story from discrete towards integrated. So typically, optical communication or optical transceivers are constructed by means of discrete components, where mainly the drivers and the laser diode or the photodiode and the front end of the receiver are made in non-CMOS technologies. There is a trend, a clear trend towards integration. And a first trend towards integration is shown here on this slide, where a photonic IC, in short, a PIC, can integrate optical components, as there are the transmitter, the optical source, the optical receiver, the photodiode, and some waveguides. Typical technologies for this are made in indium phosphides, in which we can make lasers, modulators, photodiodes. Very interesting, but it cannot integrate transistors. We cannot make transistors in this technology. And therefore, we rely on a separate electronic IC or EIC to integrate transistors. And we come to this heterogeneous integration with copper pillar bonding, as can be seen here. So an electronic IC, a photonic IC with a heterogeneous integration and a separate laser here in this situation. Very high performing systems, but of course, this is not fully integrated. A second trend is even further in this direction, where SOI CMOS processes are being modified in so-called silicon photonics processes. Of course, an SOI CMOS process can integrate transistors, as shown here, but can be modified such that we can also integrate optical components, like, for example, a waveguide or some germanium photodiode in post-processing. Now, this being a modified SOI CMOS process, these modifications need to be redone for every new CMOS technology generation. And this is clearly a costly and extremely time-consuming process. As a result of that, those silicon photonics processes typically make use of relatively old CMOS technology nodes. As shown here, this example here is in a 0.13 micrometer technology. Mainly Luxtera and IBM, now Global Foundries, are taking that approach. The third approach is what I find the most interesting, is to integrate everything in CMOS, everything in silicon. And then, of course, we can profit from bulk CMOS as a mature process, which is also excellent for mass production. Of course, there are many drawbacks. There is no germanium as a photodetector or 3,5 photodiodes. We need to work with silicon, and silicon is an indirect bandgap material. As a result, it is not very efficient to interact with light. As a result, we cannot make lasers in this technology. So this is only viable for receivers. On top of that, there is no photoelectric effect. Otherwise stated, there is no creation of electron hole pairs in silicon, in the silicon substrate material, for light in this telecom wavelength range, 1310 and 1550 nanometer lights. So for those wavelengths, silicon is transparent. Therefore, the research on those type of integration systems is mainly on 850 nanometer, for which silicon is not transparent and which is absorbed by silicon. Now, at the end of this talk, I will show you that this is indeed possible. 1310, 1550 nanometer receivers are indeed possible, not making use of silicon as a receiving material. More on that in a couple of minutes. So let's now have a look at integrated receivers for these more traditional 850 nanometer links. Let's start simple by showing the optical receiver block diagram, specifically for an integrated optical receiver, where we also integrate the photodiode in the CMOS chip or on the CMOS chip, as shown here. So we let light impinge on the front side, the top side of the chip, where it interacts with all the dielectric layers until it reaches the silicon substrate, where an NP or PN diode can then be used to convert the impinging light, the impinging photons, into an electrical current. That current is sensed and converted into a voltage by means of a transimpedance amplifier, and then an equalizer is there to boost the speed. The post amplifier is something I won't discuss today. So let's first have a look at this photodiode. The main task of this photodiode is to convert photons, light, to electron-hole pairs, a current. The most important performance parameters are responsivity, gain, how much current is generated for how much impinging light power. Of course, we want that responsivity to be as high as possible. The unit there is amperes per watt, amps per watt. The bandwidth, the optical conversion bandwidth, if we turn on the light, how steep is the current increasing at the output? That is the optical conversion bandwidth. And then there's also an electrical bandwidth, because as we will see, a photodiode represents an electrical parasitic capacitance at the input of this transimpedance amplifier, and this forms a dominant pole here, electrically seen, at the input. Also, that needs to be kept under control. Let's first have a look at silicon as base material. So we are going to convert photons into electron-hole pairs by making use of silicon. So what we need to consider here is the optical absorption coefficient as a function of wavelength. It is shown here for a wide variety of semiconductor materials, but interesting for us is this red line, which is for silicon. And what you see here is that the optical absorption coefficient is very high for very short wavelengths near the ultraviolet range, and then steeply falls to very small values for wavelengths around 1.1 micrometer, which is in the near infrared region. Our 850 nanometer light that we want to make use of is located here where we have an optical absorption coefficient which is clearly not zero, and which results in a penetration depth, how deep the light can penetrate in silicon, which is around 20 micrometers. The penetration depth is nothing else than the depth in the silicon where 63% of the light is already absorbed in the first 20 micrometers. Of course, as you can see here, if you go around 1.3 or 1.5 micrometers, silicon does not absorb this. The absorption coefficient is so low that silicon is just transparent for these wavelengths. So taking this into account, we can now have a look at this graph here, which shows the relative response as a function of wavelength for silicon. And what you see here is that the shorter the wavelength, the smaller the relative response. This is a bit strange, because here we have seen that it increases as the wavelength decreases. That is not the case here. Well, what is happening is that the shorter the wavelength, the larger the absorption coefficient, as seen here, but the less photons we have per watt of impinging optical power. So here we absorb all the photons, but we don't have a lot of photons anymore. So we have an increase, and at some point it starts to drop, because here at those wavelengths, we suffer from the optical absorption becoming very small. So there is an optimum, and an optimum is around 850 nanometers. And that's, of course, very interesting for our 850 nanometer links. So now we know how to create electron-hole pairs, but of course, we need to collect those electrons and holes. And this is done by means of an electric field that is created in a reversely biased junction, a reversely biased PN junction, a photodiode. This is shown here. So a reversely biased PN junction has a depletion region with an electric field, and this electric field will separate electrons from holes by this electric field. And as a result of that, that electron cannot fall back to the hole, so we don't see any recombination. That is the first condition for having a response, for having an output current. We don't want to have any recombination, so we want to have this electric field. We also want this electric field because it gives rise to a current that is created by means of an electric field, a drift current, which is a fast current. Electrons and holes will also be created outside of this depletion region, as light impinges on this structure. But here there is no electric field, and as a result, there is only diffusion, and diffusion is a slow process. And that is a clear limit for silicon CMOS photodiodes, is that there is a lot of diffusion current, so the response is slow. This is a very well-known problem. So we want the widest depletion region possible for speed reasons and for responsivity reasons. Thirdly, we also want to have a low parasitic capacitance for electrical bandwidths. Also from this point of view, we want to have the widest depletion region possible, because the width of this depletion region is here in the denominator of the formula for the depletion layer capacitance. So if we have a look now at this formula for the depletion layer capacitance, we see here two parameters that we can more or less influence. All the other parameters we cannot influence because we work with silicon. We work at room temperature typically. So the only parameters we can influence are the doping concentration. We don't have that fully under our control, but we can choose layers. We can choose N+, P+, P well, N well. They will have different doping concentrations. So we should choose layers with the lowest doping concentrations. And that is the reason why the majority of high-performance silicon photodiodes makes use of the substrates, the P-type substrate typically, and a well, so not an N+ diffusion. Secondly, we can also influence this parameter, the reverse bias voltage. We want to have the highest reverse bias voltage. Typically, we want to have this here limited by the supply voltage of our device. Now, there is another thing that we need to consider if we work with silicon CMOS photodiodes, and that is what is called the optical transmission coefficient. Light impinges on a photodiode, N-well to P-sub photodiode, but in between the light exiting a fiber, which can be located here on top, there are several dielectric layers which the light needs to pass first. And these dielectric layers have different optical properties because their epsilons, their dielectric constants, are not all the same. So this is a structure that we need to investigate first, and that is what we need to understand first. So the light needs to pass this dielectric stack, and we need to calculate the transmission coefficient, which is the fraction of photons that will reach the silicon substrate. Of course, we want to have that transmission coefficient equal to 100%. What is important to do this is first to calculate what is the intrinsic impedance of each of those dielectric layers. The intrinsic impedance, eta, is nothing else than the ratio of the permeability and the dielectric constant. Or typically this permeability is 1, so it is 1 over the dielectric constant of the dielectric layer. Now, you may not forget that the dielectric constant is in general a complex number. We typically only consider the real part, but if you go from DC up to optical frequencies, there are regions of frequencies where the dielectric constant becomes complex, and this complex part indicates that the dielectric layer becomes absorbing, starts absorbing your photons from that particular frequency. Now, the way or the reason why that is important is that typically a PDK or a foundry gives dielectric constants for DC or relatively low frequencies up to gigahertz frequencies, which is here. This is not what we need to do our investigation. We need to have the values here at the optical frequencies, which is a lower dielectric constant due to the absorption peaks, the dipolar and ionic absorption peaks that happened at lower frequencies. So this is important to realize to do the further analysis. Once you understand that, now we can analyze what is happening here. And indeed, what is shown here is a dielectric stack for a relatively old technology. I think this is a 130 nanometer dielectric stack. So we have the silicon substrate of 280 micrometers thickness, an N-well with a thickness of around 1.5 micrometer, and then all the dielectrics. They're not all the same. They each have their own dielectric constants. And as a result, they each have their own impedance. And as a result, there will be many reflections going on. So we need to calculate what is the reflection coefficient between two layers, gamma from 1 to 2. And that is nothing else than the difference between the intrinsic impedance divided by the sum of these intrinsic impedances. Now, of course, we have many, many layers, so we need to do this iteratively, as shown here with these formulas. So this is a recursive calculation, and if you do this with some assumptions for the technology, this is what you end up with. So this is a calculated transmission coefficient for a 130 nanometer CMOS technology, the stack of which was shown in the previous slide. So we calculated there the reflection coefficient, but we are interested in the transmission coefficient. Well, of course, the transmission is nothing else than 1 minus the reflection coefficient squared. And what we see here is that the transmission coefficient is indeed an extremely strong function of wavelength. We are most interested in 850 nanometer light, which might happen to be or to have a high transmission coefficient, which is good. But if the thickness of one of the dielectric layers due to manufacturing differences is going to increase or decrease a bit, this peak here might quickly become a valley. And you end up with a very low transmission coefficient. And there is nothing you can do against that. A lot of this information, by the way, is confidential information by the foundry. For example, the number of these dielectric layers, the thickness of these layers, all these constants. This is undisclosed material. So this brings a lot of uncertainty at design time and is clearly a disadvantage if we want to go for a front-side illuminated photodiode where we impinge light on the top of the silicon substrate. This can also be measured, by the way. So this is shown here. The plot on from the previous slide is repeated here. This is the transmission coefficient of the dielectric stack. This is also shown before. This is the intrinsic response of silicon. If we multiply the two, well, this gives rise to this, but this is not just a multiplication. This is an actual measurement where we swept the wavelengths and measured the response, the amps per watt impinging light power. And a similar type of behavior, although not so fine, not with such a fine resolution as here in this calculation, is seen here. And these numbers going up and down so strongly is nothing else than the effect of the dielectric stack. On top of that, so this was about the response, the amplitude of the current coming out of the photodiode. On top of that, CMOS photodiodes are slow. And this is seen here. So here is a cross-section of a photodiode in CMOS with an N-well and P-sub photodiode where there is a depletion region here and light impinges. And if you still remember, the penetration depth of light of 850 nanometers is around 20 to 25 micrometer. So only in this region, we have absorbed 63% of our light. So this goes slowly. If you have a look what the fraction of the light of the photons is that is absorbed in this region where there will be drift, that is only very, very modest. Only this fraction of the light will give rise to drift current, which is fast. This drift current here in the gray line is fast. The bandwidth is basically infinity, or at least it is not visible in this limited frequency range that we plot here, but it is also a small current. The biggest current is, of course, this bulk of photons that is absorbed in the substrate. That is the biggest fraction of the current is originating from there. Electrons created here in the substrate, but of course these need to diffuse until they reach the depletion region, and this is very slow. As a result, the bandwidth is very narrow as well. We're talking about bandwidths between 10 megahertz and 100 megahertz. Typically, we assume around 10 megahertz bandwidth. And this, of course, makes it impossible to achieve high data rate applications. Researchers have proposed many solutions to this well-known problem. The first very interesting approach is a so-called differential CMOS photodiode. A cross-section is shown here. And an alternating pattern of illuminated and non-illuminated N-well P-sub junctions is shown here. These black bars are metal 1 stripes, which block light from creating electron hole pairs below the non-illuminated junctions. This might seem strange, but it's actually a very clever idea. Because, as still know diffusion is happening here for these electrons, and those deeply generated electrons will diffuse to a region where they want to be, and one of these regions is this junction. So although there is no direct light impinging on these non-illuminated junctions, some electrons will still diffuse towards these regions. And there is a theory, it is proven by these people from VUB in Brussels, that if you make the repetition rate, WP, narrow enough, that from a certain depth onwards, the chance that an electron goes to a non-illuminated junction is as large as the chance that the electron is going to diffuse towards the illuminated junction. And as a result, if we now make a difference, if we take the difference between the current from the non-illuminated and the illuminated junctions, the effect of these slowly diffusing electrons disappears, and we go towards much higher frequencies, much wider bandwidths. So this is the main idea. Of course, the main drawback is that 50% of the light is reflected. Perhaps you can make a better approach here, and that is shown here. I call this the Ppeed-enhanced photodiode, and we published it a couple of years ago already at ESSERC. There is no 50% light reflection because there is no metal coverage here. What is here instead, to remove these slowly diffusing electrons, because we still want to get rid of those, is an electric field in the substrate. So we create electric fields in the substrate currents, very local, by making a voltage difference between two P-wells. This creates an electric field, and now these electrons will follow this electric field. And deeply created electrons have a high chance to be drained away in this P-well, never reaching the junction. So they will also not influence our speed. And again, speed increases and these slowly diffusing carriers are removed. Let's now discuss the transimpedance amplifier. The duty of the transimpedance amplifier is to convert the current into a voltage that is called transimpedance. People also call this gain, but this is not really a very well-chosen name here. We are, of course, interested in bandwidth. That results in input impedance. Noise is important because the currents from a CMOS photodiode are small, so we need to have a low noise transimpedance amplifier. And of course, we also want to have a low power consumption. The simplest approach is to make use of a single resistor transimpedance amplifier. We let the current of the photodiode flow through a resistor and a voltage will appear here. That's very simple, it works. The transfer function of the simple circuit is shown here. The transimpedance is indeed nothing else than the resistor RTIA, and the bandwidth is determined by the time constant RTIA, and then with the C photodiode, CL, the load capacitance, output capacitance. We can multiply those two numbers to come to what is called the transimpedance bandwidth product, just like the gain bandwidth product for an op-amp, but now with a transimpedance amplifier. And we see that here, the transimpedance RTIA is not part of this equation. And the transimpedance bandwidth product, which we want to maximize typically, cannot be changed. It is determined by our photodiode capacitance. So we don't have any design freedom here. Moreover, so this leads to this red dot here, the fixed transimpedance bandwidth product. This is not something we as a designer like. And next disadvantage is that the photodiode reverse bias voltage depends on the value of this resistor, the supply voltage, and the average current that the photodiode has. So it will change with impinging light power. And that is also something we don't like because we want to maximize the voltage across the photodiode to minimize C photodiodes. But of course, there is no power consumption. There is a resistor that gives noise. And for a certain bandwidth of 1 gigahertz, that noise will increase because RTIA needs to decrease to maintain a bandwidth of 1 gigahertz if we increase the photodiode capacitance. Therefore, it is easier to work with smaller photodiodes or with photodiodes with high reverse voltages, having a small photodiode capacitance, because we end up with lower input reversed noise currents. We can go a step further by means of a cascode TIA. Now we try to decouple the resistance, the resistor RTIA that converts the current into a voltage from the photodiode capacitance by putting a cascode transistor in between. Now the input impedance is not RTIA, but is 1 over GM1. And as a result, we can, as a designer, freely choose what GM1 is going to be. And this GM1 now determines the bandwidth. The transimpedance is still given by RTIA. The transimpedance bandwidth product, ZBW, is now composed of GM1, RTIA, and the input capacitance, which is as shown here. Advantages are that the photodiode reverse bias voltage is constant, and there is design freedom for transimpedance bandwidth products. But of course, we have more noisy components. We have 2 transistors, and as a result, we end up here for similar requirements with typically a higher input referred noise as on the previous slides. We can go even one step further by making use of a regulated cascode TIA, where we have M1 now with a varying gate voltage, that is an inverting amplified version of the source voltage, to boost the GM of transistor M1. As a result, the transimpedance bandwidth product also includes this extra gain from this extra stage, ARGC, which is nothing else than the GM of MRGC multiplied with the load resistance here. And indeed, we can boost this product, so we have even more design freedom, but we have even more noisy components, so even more input referred noise. On top of that, this is now a closed loop system, so we need to guarantee stability. A shunt-shunt feedback TIA is, I would say, the most interesting approach for integrated CMOS photodiodes. Is also the most used approach for integrated CMOS photodiodes. It is shown here. So we make use of a wideband voltage amplifier with negative feedback, and we have a resistor here in the feedback path. And we have again our photodiode here at the input. The transfer function is composed of 2 poles, one here at the input, one at the output. Since the photodiode capacitance is typically a very large capacitance, the input pole typically determines the bandwidth, as shown here. RTIA Cin multiplied, divided by A is our time constant at the input, so this determines the bandwidth. And again, the transimpedance is just as before, given by the value of the feedback resistance. The transimpedance bandwidth product is A over 2 pi Cin, and again, we have design freedom if we can make a voltage amplifier with high gain. Not only high gain, also low R out. It needs to be a wideband amplifier, because otherwise the dominant pole will appear at the output, and then these equations are not valid anymore. On top of that, we also need to be careful in the design of this amplifier, because it typically will determine the noise, as is shown here. The input referred noise, again, as a function of photodiode capacitance, in total here in the black line. The noise of the resistor, the feedback resistor RTIA is shown here. All the rest here is created by these noisy transistors inside the voltage amplifier. So we need to be careful how to design and size this amplifier. And lastly, we need to be careful because this is a closed loop circuit, so it can become unstable. We can go a bit deeper in detail in this noise. So now we plot the input referred noise as a function of the CGS of the first transistor of this amplifier, M1, I call this. So we can sweep this transistor from very small values, low power consumption, low currents, small GM, large input referred noise of the voltage amplifier, and as a result, large input referred noise currents of the transimpedance amplifier. As we increase the input device, the CGS, the W over L, we increase the current, we increase GM, we reduce the input referred noise up to a certain point where the CGS of the input transistor starts dominating the input capacitance. Because of course, if the input device becomes so big that the CGS becomes in the order of magnitude as a photodiode capacitance, and if we want to maintain the same bandwidth, we need to start reducing the value of RTIA if we go further in this direction. And as a result, in this region here, we are limited by an increasing RTIA. Yes, we have very low noise of our voltage amplifier, but we need to reduce the value of our TIA to retain bandwidth, and as a result, the input referred noise current goes up again. Optimally, we want to end up around 0.4 to 0.6 times C photodiode for CGS M1. This voltage amplifier needs to be designed, of course. It needs to have high gain, stable gain. It cannot be an op-amp that just has high gain. We need to have the gain stable because it determines bandwidth. It is in the formula for bandwidth. So we need to have a stable, well-known gain. It also needs to have a high bandwidth, low noise, low power, low input capacitance, very challenging design. So starting simple, we can start with a common source amplifier, or what I call a double common source amplifier, where here we have a small input capacitance, a low voltage gain, relatively high input referred noise per watt power consumption, while this stage has a higher input capacitance, double the voltage gain, and a lower noise per watt. Even though this seems to be more interesting, especially for the first amplifying stage, in recent CMOS technologies, a single stage only gives you a factor of 4, 5, 6 of gain. And as a result, this is not enough to have wide bandwidth operation. So we cannot survive with only having a single stage. So we will cascade gain stages. This is shown here. We will cascade low gain but high bandwidth stages, as shown here. The gain of the cascade, the DC gain of the cascade, is nothing else than the gain of a one-stage amplifier to the power of n, n being the number of stages, and the bandwidth is equal to this relatively complex number, where we have a bandwidth of one stage that is reduced the higher the value of n. But still, the gain bandwidth of the cascade can be increased significantly, as shown in this formula, as n increases, because we profit more from this green part increasing than what we suffer from this red part decreasing, on the condition that the gain of a single stage is higher than 1, as shown here. So one of these here, but not with a gain of 1. So this is the idea. On top of that, we can do inverse stage scaling to reduce power consumption, to increase bandwidth, because this stage will be smaller than this, so the bandwidth here on this node will increase. And we can do that because the noise of this first stage is the only important one. Then there is a self-compensated transimpedance amplifier. This is a published ID from several years old. This is a speed enhancing technique where the voltage here is copied to the anode of the photodiode, so that there is no voltage difference across the photodiode capacitance, and as a result, the bandwidth is not determined by this photodiode anymore. This works, but now there is a new limit, of course. That limit is created by B, the output resistance of B, and the photodiode capacitance. So our TIA does not determine the bandwidth anymore, but now we have here a loop. We want to have a gain of exactly 1. Is the gain a bit higher than 1, then we have an oscillator. So stability is very hard to achieve here. On top of that, B is a big unity gain buffer that determines the noise and consumes a lot of power. And lastly, since the anode for CMOS photodiodes is a silicon substrate, that node is not accessible to us. So a better way is the capacitance-relieved transimpedance amplifier, as shown here. We make use of the negative Miller effect around the capacitor with positive amplification around the capacitor to create a negative capacitance here, which is in parallel to the photodiode, to tune out this photodiode capacitance. Basically doing exactly the same, namely boosting the bandwidth, as shown here. If we balance C TIA with C photodiode over A, we go to a bandwidth of infinity, mathematically speaking. Again, we have stability, a potential stability issue, because if the capacitance here is overall negative, we have an oscillator. But now B does not create a lot of noise, and there is also no anode access required, which is of course now possible for our CMOS photodiodes. Let's have a short discussion about the equalizer. As discussed already, the photodiode conversion bandwidth is very modest. It can be increased a bit by making use of a differential photodiode, but it's still relatively modest if you want to go towards gigabits per second communication. Now, luckily, the roll-off of photodiode is relatively modest as well because it is a distributed system. This is not minus 20 dB per decade. It is only minus 5, minus 4 dB per decade. As a result, there is still a relatively big signal here. So we can boost this signal to here by multiplying this with a low roll-up equalizer. How can we create such a low roll-up equalizer? Well, that can be done by adding, not by multiplying, but by adding first-order filter branches, high-pass filter branches, where we profit from this lower than 20 dB per decade increase on the knee of those filters. And by then properly putting the poles of these high-pass filters and the weights of these filters, we can create an equalizer transfer function, which is exactly the opposite of the transfer function of our photodiodes. This has been proven several times to work properly. The first one was Professor Bram Nauta from Twente, where indeed, without an equalizer, you can go to a data rate of several tens of megabits per second, because the bandwidth is only 10 to 50 megahertz, the conversion bandwidth of the photodiode, but with the equalizer, you can go to gigabit per second communication. This was a single-ended approach. Here you can see a fully differential approach where there is a differential photodiode, a differential transimpedance amplifier, a differential equalizer, and the speed is boosted to 4.5 gigabits per second. Here you can see some circuit diagrams, a fully differential transimpedance amplifier with 2 feedback resistors, and fully differential amplifier that's interesting to collaborate with the differential photodiode, because a differential transimpedance amplifier boosts the differential mode and rejects the common mode. And that's exactly what we need for the differential photodiode. We need to subtract the 2 currents, we need to reject the common mode and boost the differential mode. That's exactly what the circuit is doing. Here you can see the equalizer. It's also a differential equalizer now, where the filter branches, the high-pass filter branches, are constructed by means of frequency-dependent source degeneration here by these filter branches. And this has then resulted in 4.5 gigabit per second communication. Other groups have worked further on this idea by having slope detection equalizers to further boost speed to around, I don't know where it is here. I think this is an 8.5 gigabit per second, 8.5 gigabit per second receiver. That is currently still state of the art. Let's now have a short discussion on integrated receivers for this other wavelength band, the more traditional telecommunication wavelength bands, 1310 and 1550 nanometers. So in order to do that discussion, we need to use a different type of device, because a PN junction clearly won't do the job because silicon is transparent for these wavelengths. A device we have been investigating for this purpose is a so-called Schottky diode. A Schottky diode is not a silicon-to-silicon diode, but it is a metal to semiconductor, or in our case, the metal to silicon junction. This metal layer that we will use is the silicide layer, which is deposited here on top of the silicon substrate here in gray. And then we make a junction to our substrate or to a well. So the green line here is now our junction. In the previous discussion, we were talking about this junction here, the PN junction. Now we're talking about this junction here. Now, in order for this to be a junction, we don't want here to have an ohmic contact. We need to have a lowly doped region here. This cannot be a diffusion region. It needs to be a well or a substrate, lowly doped, so that we have a junction with a band gap, phi b, the Schottky barrier. And indeed, since we have this barrier, this behaves as a diode, as we will see directly. This silicide depends on technology. It is also not disclosed by the foundries, and it depends on scaling as well. So in older technologies, the foundries used titanium silicide, then they went to cobalt, and I think now they settled on nickel silicides. This is also undisclosed information, so this is very hard to model up front. But that is also the reason why we took the approach of making use of measurements to do our modeling. More on that on the next slide. But first, let's have a look how such a device can work as a photodiode. So on the left, what is shown here on the left is our traditional approach where we absorb a photon by creating an electron-hole pair that is swept by means of an electric field left and right to create a current. The photon needs to have an energy which is at least the silicon band gap, and that leads to it being possible for 850 nanometer, but not for this wavelength. On top of that, due to the deep penetration of this light, we end up with a slow response. Now, we are not going to absorb light in the silicon, we are going to absorb light in the silicide, so the metal-like layer. This is a technique or a principle which is called internal photoemission. And this technique works for photons with an energy that are larger than the Schottky barrier, so that free electron in the silicide can jump the barrier and flow towards the silicon to create a current. And now, since this Schottky barrier is lower than the bandgap energy of silicon, we can now also operate our systems with these wavelengths. Moreover, we have a very localized absorption, not deep in the substrate, but local in the metal, and this ends up in fast response. So this is very interesting. But as I already said, those are not native devices, so we needed to do a lot of modeling ourselves. And this is shown here. So an example of one of our test structures is shown here. So many photodiodes that we tried with several layouts, where we have here the silicide in purple, and then the metal to contact this side of our photodiode. The well here is our other contact, the anode, the N well. And of course, since we make use of wavelengths for which silicon is transparent, we make use of backside illumination. So we send the light through the silicon substrate to our structure. Because of course, if you would go from the front, we would need to pass this metal layer, and this wouldn't be possible. So these are non-native devices in CMOS, and of course, we want to do our modeling. So we want to end up with values for all these components. So this is the first task that we try to do. One of these experiments is shown here. First, for the electrical characterization. What is seen here is as a function of the voltage reverse and forward, how the current is varying in these devices. And we clearly see here an exponential increase of the current. This is our diode behavior, where at some point we have saturation. And here we have reverse currents flowing. From those values, we can end up, or you can deduce values for RD and RS, the series resistance, which is indeed quite small. And also we can end up with values for CD with S parameter measurements. So this allows us to fill in those gaps in our model, but we still don't know how big of a signal current we will have as a result of impinging photons. For that, we need to do optical characterization, as shown on this slide here. So what we did is we made use of backside illumination of an integrated Schottky photodiode in CMOS, and we impinged light of 1310, 1550 nanometers as a function of optical light power. You see here the current that is flowing out of these devices. The more current, the more light power, the more current. And this happens in a more or less linear fashion as expected. The currents coming out for 1550 nanometer light is a bit smaller than for 1310 nanometer light because the photons are more energetic here. So they have a higher probability to release an electron in the silicide that can jump the Schottky barrier. And now we have all components filled in here, and we can try to make fully integrated receivers that are sensitive to those wavelengths. Now, this is something that I will not discuss in much detail because it's a very complicated matter. If you want to have more information, I refer you to this recently published paper that we did. The idea here is that since we enter the silicon through the back, and we end up here with our silicon substrate, with our Schottky junction, then we have the silicide, and then all our metal layers and our dielectrics, we will also have a lot of reflections going up and down. We made use here of flip chip bonding. So even our PCB here can be a source of reflections that light enters and comes back. And that can give rise to constructive, but also destructive interference. as shown here. This is a very similar story as what I explained to you in the beginning for CMOS photodiodes, where we entered at the top. Here we see a comparable problem, but also when we enter at the bottom. Now, of course, we can have a solution to this, and that is with the M1 shield. So we just cover, we basically shield this whole structure by having a metal plate here in M1 to completely reduce these oscillations going on. And now the only thing we have is a beat period that depends on the thickness of the silicon substrate, because now there will be reflections between air silicon and silicon silicide interfaces. And the pattern or the repetition rate depends on the thickness of the substrate. If we go towards wafer thinning, then we can reduce this beat period and have less sensitivity to this absorption ratio, for this absorption ratio. And this clearly is the way to go here. So now there is a way to reduce, to remove these dependencies on the of the transmission coefficients. This is our first implementation of a Schottky-based optical receiver in 40nm CMOS, where here you see a Schottky diode, a full differential transimpedance amplifier that also makes use of negative Miller capacitance here to increase the electrical bandwidth to reduce the parasitic capacitance here. There is no equalizer, as you can see, because we don't need it, because our photodiode is so fast, we don't need to boost the speed. We will be limited by the electrical bandwidth. So this saves power and area. So we can directly go towards a limiting or a pulse amplifier and a buffer. It's a very small thing, a full optical receiver, fully integrated in 40nm CMOS without any process modifications. And by making use of a variable feedback resistance, we can modify bandwidth for noise, and this is in measurement. The gain can be high for a narrow bandwidth, or the gain can be low for a wide bandwidth. Now, of course, at some point, the system becomes unstable and we start seeing some peaking here in the gain transfer function. Speeds up to 1 gigabit per second were achieved. And this was the first showcasing of a fully integrated receiver with the Schottky photodiodes. We went further and went to 28nm CMOS, doing something very comparable, but now making use of another type of transimpedance amplifier, where our first stage is composed of a structure that can create a negative impedance here and on the load nodes, so that the gain can be traded for bandwidth by varying the value here of this resistor R2. If we vary resistance R2, we can change gain for bandwidth, for a fixed gain bandwidth of this first stage. The typical approach is to have this stage with a relatively modest gain but wide bandwidth to create dominant pole here. Now, the idea of this chip is to make the TIA underdamped, to have a high gain but low bandwidth first stage to profit from a better achieving transimpedance amplifier. And indeed, the analysis shows that the high gain, low bandwidth first stage amplifier, giving rise to an underdamped TIA behavior, allows us to end up with a higher bandwidth and the lower input referred noise current. The red line is below the blue line, and that's better behavior. And that we'll also be able to show in small signal measurements, where the dotted line is the traditional approach, high bandwidth, low gain first stage. The thick line, the solid line, is the high gain, low bandwidth first stage. And clearly, we gain bandwidth with about a factor of 2, 1.8, depending on the actual value of our feedback resistance. So let me now conclude and show you or explain to you what is the intention for future work. So as a conclusion, optical receivers in CMOS are possible. Mainly, the research efforts are focused on 8 and 50nm receivers. Our novel results also prove that 1310 and 50nm receivers are possible, making use of Schottky photodiodes. Now, regardless of whether you use 850 or these receivers, we always have low responsivity of photodiodes because of the intrinsic nature of silicon and the Schottky diodes, which require low noise readout circuits. So this is, of course, extremely important. For future work to have better performing receivers, what we want to do is increase speed and sensitivity. For the Schottky diode, that means making use potentially of different materials, other technologies, other types of structures, layouts. This is work under development. For the transimpedance amplifier, that means improved, better optimized circuits, perhaps even going towards decision feedback receiver architectures. We currently have a chip like that currently under investigation. And of course, you can think of making use of Schottky photodiodes for other types of applications. Now we are sensitive to infrared, so we can think of infrared imaging in CMOS, or doing rectification of terahertz frequencies fully integrated in CMOS. This is all under development. And with that, I would like to conclude my talk. Thanks a lot for your attention, and I'm open for any questions you might have now.
Thanks, Professor Tavernier, for this very, very interesting talk on the roadmap on these integrations of the receivers, which is a very hot, important topic for optical communications. We have our viewers here in the internet land that have some questions. The first one is from Murilo Passati, who heads the CMOS Microelectronics here in Brazil. Congratulations for a very good talk. And question is, do you still see a space for silicon germanium by CMOS process, its need or usage in some receiver applications, or CMOS is still, or shortly will be the choice for almost all the majority of these applications on receivers, optical receivers? So what do you comment on that? Silicon germanium is still being an option for high performance.
Okay, yeah, thank you for this very interesting question. Long story short, no, I don't think that CMOS will replace those technologies, because those technologies, they allow you to do a much better optimization of your optical receiver. So I still see a big use case for those technologies. There's more expensive, more higher power consumption technologies and approaches in silicon germanium by CMOS for extremely high data rates. So if you want to go towards several hundreds of gigabits per second, use those technologies. But if for consumer applications, bandwidths don't need to be so high, but you're more interested in manufacturability, in size, in power consumption, in integration with your digital backend, then this might be a viable approach with the structures that I've explained here. So no, I don't see this as a direct competitor for silicon germanium by CMOS.
Okay, another question that goes in the same vein, same line of thought, is from Anish Yoshi. Thanks, Anish, for the question. The question is, how are the photodiode for 20 gigabits per second or plus or more different comparing to the structures that you have discussed today? In which way they are different?
Yeah, so there they make use of discrete components. And those discrete photodiodes, they are made with very special exotic materials. So that can be InGaAs, where they use reverse voltages of several volts or even tens of volts to create very wide depletion regions to capture all of the photons in a region where there is drift. This is not possible in silicon, in CMOS. It is possible in silicon, but not in CMOS. So that is the main reason why those photodiodes can achieve much higher data rates. Those options are not open to someone who would like to do a full integration in CMOS. There are other limits, which are completely different with discrete components and different materials.
Okay, another question comes from Professor Van Nooy from University of São Paulo. He's the head of the solid-state secret chapter in São Paulo. He thanks you for a very interesting talk. And he's asking, in the 115 nanometer photodiode design, you could include the layout geometries on different levels so that the dielectric layers should be removed step by step during the processing. Is this possible?
I think the question is whether those dielectric layers can be removed somehow.
Yeah,
yeah. Excuse me?
To cope with the reflectivity, I believe, yeah.
Yes. Well, yes, that is possible. But it is a very expensive and difficult to control post-processing step. So if the idea is to put this optical receiver next to your digital backends, and you just want to not to do anything special in your production of these chips, you don't want to have an expensive etching step to remove all those dielectric layers. Yes, you can do that. It works. People have shown that. but I wouldn't consider that to be standard processing. That is also what I like of this second idea of 1310 and 1550 nanometer. There you can make use of the backside, and you can completely remove the effect of the dielectric layers. So you don't have the problem there of all these dielectric layers. So yes, you can do it, but it's an extra processing step, and it depends on what you're most interested in.
Okay, I have a follow-up on that. In this 1310 and 550 integrated receivers, is there a limit on the thinning? You'd like to go, the thinner bulk at the end. What is the range of thicknesses for the ultra thin on the book Schottky process that you advise it's possible to do? I know all your research is trying to make this receivers integrated on as close as possible standard CMOS, but the wafer thinning in the end, how thin can you go? And would you like to go thinner?
Well, that's a technology question. I don't know that. We have a grinder in our in-house laboratory to try to do that. It is not a production type of machine, but we can investigate. By the way, all the results that I have presented today are on wafers that were not thinned. So I believe that if we further explore on this idea, because this is recent material, that we can still improve our responsivity, improve our SNR, reduce bit error rate for an input light power. So I don't know how thin people can make chips. But what we have shown here is that it already works for chips that are just coming from the foundry as they are, with thicknesses of 250 to 300 micrometers. But we believe that if we are going too thin, that we can still improve our performance. But it's about absorption peaks. So you might end up here, or you might end up there, and it can be a peak and a valley. You don't know that. You don't know that beforehand. That's uncertainty. But we have seen that with all the chips that we have, the responsivity is good enough to show already the results that we have here. So the thinner you can go, the better. I don't know what the limit will be. I think in-house we can go to 50 microns, but I think perhaps in production they can go thinner than that.
Okay. Another question is in terms of this, if without thinning, trying to do the standard Schottky, did you do any let's say process variants and tuning to get the best possible speed? And today, with this, the trend and the current state of the art, without resorting to silicon germanium and discretes, what's the best speed? Is that of the order of 2 to 3 gigabits per second? Can you comment on that? With the decision feedback receiver, would you like to push that further to how many gigabits per second?
Yeah. So what we currently we are in the region of around 5 gigabits per second. But now we are, so for these Schottky photodiodes, compared to the silicon photodiodes, we are not limited anymore to the conversion bandwidth from light to current, because the absorption is very local. So there is no bandwidth limitation, especially not for these relatively modest frequencies of gigabits per second. We are mainly limited by responsivity. We only see microamps coming out of these structures because the absorption is local. A lot of the light will also be reflected. You may not forget, you're trying to excite electrons in a metal-like structure. If you think about that, metal is reflective by nature for light. So the majority of light will be reflected. Some light will give rise to an electron that gains energy in that metal and can then jump across the Schottky barrier. So we are mainly limited by sensitivity. So that is one of the reasons why, for the moment, we cannot push the operation speed of our circuits so far, because that's a trade-off. If we make it faster, then we make it much less sensitive. And we are limited by the power, the optical power that we can create and send through the back of our silicon photodiode. So typically those laser diodes, they give powers of around a milliwatt, couple of milliwatts. And in that region of optical power, we end up with a maximum data rate of around 5 gigabits per second. If we can have more light power, we can have another trade-off and go to to higher gigabits per second. That is something we didn't do yet because we don't have those components yet. So it depends how much. If you have more input power, you can go to higher data rates. For the moment, we are not limited by conversion bandwidth for the Schottky photodiodes. We are limited by an SNR trade-off.
Okay, we have 2 more questions and then we go finish. One is comes from Pedro Toledo. He also congratulates you for the very good talk. His question is, could you comment more about the trade-off between noise and power and gain bandwidth? He missed the power consumption during the presentations. How minimum the power consumption could be for those 3 gigabits that you just presented?
Yeah, well, that's a very long story. I will go back to slide 31 for this. Well, this is basically here. So if we assume that we want to have a wideband voltage amplifier here that is composed of several stages because a single stage cannot provide us with sufficient gain. So we need cascading. And if we assume that in that cascade, we are going to be limited by this first stage, then the optimum is here. The optimum is here because it all depends on the photodiode capacitance. If you have a small photodiode capacitance, you can have a small input transistor that ends up with a minimum input referred noise. And with a small input, with the first input, small input transistor, you end up with a low power consumption. On the other hand, it also depends on the technology that you're making use of, because this does not depend on technology here, this optimum. It depends on your photodiode. And so the size of the input transistor is typically quite large because this is a typical value of a pn-photodiode, but also of a Schottky photodiode. It's in the same region of ballpark, around a picofarad or a bit more. So that means 400 to 600 femtofarad. As a CGS of the first stage, that's a big transistor. And that's the reason that those first transistors, we typically design them in weak inversion. Because especially for the speeds that we are able to achieve with those photodiodes, CMOS is fast enough to bias it in weak inversion while still not being limited by the speed of the first transistor, still being limited by the speed of the photodiode. Okay? And the reason for that is that these are high values, 400, 500, 600 femtofarad, big transistors. If you put them in strong inversion, well, a lot of current, we don't want that, so we put them in weak inversion, and we only put the stages that come after in strong inversion, where we profit from speed. But those stages are much smaller, so we don't suffer from the current flowing here.
Okay, well, the final question then comes from Anish Yoshi. Thank you for the previous answer that you gave. His question is, how do you think the 3D integration of CMOS optoelectronics will proceed in the future? Basically, where you want to do the 3D then, integration of the optoelectronics. Well, and what are the possible applications, let's say, for an AI processor application? That's where these 2 questions.
Yeah, so as shown here, so this is a full optical receiver. The current chips that we make are optical receivers, so we continue to scale these things down, and they become smaller and smaller. Currently, we can make a full optical receiver, including the Schottky photodiode that fits within the size of a bond pad. So this is basically going to be an IP block that is plug and play. You put it somewhere on your chip, it doesn't consume a lot of power, a couple of milliwatts. You can receive several gigabits per second data communication optically, so it doesn't fight against your electrical bandwidth that you have, and you put them everywhere in your digital CMOS process without any process modification. It will be small, low power, and you can put them wherever you want.
Okay, well, that brings to the end. I thank you, everyone, for being out there in the internet land and listening to the talk. Stay tuned to this chapter, South Brazil chapter channel. We'll post there the next seminars. And I advise you that, at 26, 27, and 28 of August, there will be 2 keynotes in the Brazilian SBCCI Symposium, which will be online, and you can see the program. We'll have 3 interesting keynotes. One on the 26th will be in terahertz circuits given by Professor Kenneth O from University of Texas, Dallas. That will be broadcast from the SBCCI channel. Stay tuned. And we'll post for the September talks. I would like so much to thank you, Professor Filip Tavernier from Catholic University of Leuven, to summarize in such a clear way the path to doing those integration. We can see the potential of those advancements in terms of making these receivers something that is done on standard technologies with very fast speed, and we know that making simpler and closer to the standard technology will make those things more impactful indeed.
Exactly.
Thank you very much.
Thank you for the invitation. Oh yeah, no, I would like to thank everybody for his or her attention, for the nice questions, and for your time.
Okay, so that closed our webinar, and I wish all the safe, and we'll see you in the next webinar talk. Stay tuned for solid state circuits webinars and for the chapters. Thank you very much to all of you, and thank you to the speaker indeed for his very excellent presentation. Good night, good day.
Thank you.